In question 5, part A, we are to explain in terms of the structures and bonding why nitrogen oxides are usually only produced in the condition as described above. Okay, so what is this condition? So we are looking at N2 and O2 in the atmosphere reacting to form NOx during lightning strike or in internal combustion engines, all right? So the large amount of energy is required, right? Because you need to break the strong N triple bond, covalent bond in the nitrogen gas. Take note, if you just say that the activation energy is high, all right, and this will not be enough because the question asks for structures and bonding, so you need to bring in the bonds, triple bonds in the nitrogen gas. In part B, you are asked to state one other undesired consequence of the presence of NO in the atmosphere. Okay, so this is a very factual questions, right? You can either say NO trigger respiratory problem or it can cause ozone depletion. Now, this is actually a legit question, not a general questions or anything under the sun that we are having, but it is stated in the syllabus for alkanes that you need to be able to recognize the environmental consequence of carbon monoxide, oxides of nitrogen, and unburned hydrocarbon arising from the internal combustion engine and the catalytic removal. Okay, so this is in the syllabus, must know. Okay, part C, we will start having a reaction now. This is a reactions between nitrogen monoxide, NO, with chlorine gas to give NOCl. So generally when we have rate equations will take in this form where rate equals to rate constant K times concentrations of the reactants raised to their respective order of reaction, okay, which is some power. So because we have NO and Cl2, therefore our rate equations, it should have two concentration term at least, unless we have order 0. So from the questions, we are told that there is a constant half-life of 10.8. So this tells us that it is a first order with respect to NO. You are given directly that the order with respect to chlorine is 1. So therefore, putting this, the power of both concentration term is 1. Therefore, rate equals to K concentration of NO times concentration of Cl2. Now, you are reminded that the rate equal must be present, okay, in your rate equations. Otherwise, it's not an equation. You cannot just put K times the 2 concentration. That is not an equation, that is an expression. Okay, so rate equal must be there in your answer. In part 2, sketch the expected shapes of the two graphs. Okay, the two graphs that you need to sketch is graph A, concentration of NO against time. Graph B is rate against NO. Okay, graph of rate against NO. So how do we use the information provided to sketch the graph? Okay, let's run through them. So in the first part, when we look at graph A is supposed to be a graph of NO against time. You know the initial concentration is 0.100 mole per dm cube. The constant half-life is 10.8. So meaning when I start the experiment with 0.0100, okay, by the time when I hit the concentration, it falls to 0.0050. This will take me 10.8 minutes. For it to half again, to become 0.0025, this will take another 10 minutes. So using this piece of information, we can now try and figure out the shape of the graph. Okay, remember the half-life is a constant. So this is my first half-life, 10.8. this will be the second one, another 10.8. So the graph will be a curve. Okay, we can see that this is actually a curve. Next, graph B. This is a graph of rate against concentration. We are told that the concentration of chlorine remain constant. Okay, therefore, this means that I can group K and the concentration as K prime. I will now rewrite this as a K prime concentration of NO. So if I plot the graph of rate against concentration, can you see that my graph now follow a relationship y equals to mx, where y is my rate, x is my NO. And what is K prime? K prime is my gradient. So this will be a straight line graph passing through the origin, right? And my gradient is equals to my rate constant, K prime, and this is equals to K times Cl to concentration. Next part is explanation of the term half-life. Do take note that there are quite a number of terms that you need to be able to explain for this topic. You might want to refer to the first page of the lecture notes, the learning outcomes. It will tell you what are the terms that you need to be able to explain in the for the assessment. So what is half-life? Half-life will be the time taken for the concentration of a reactant to be halved. All right. Next, to determine the time taken for nitrogen monoxide to reach 10% of original. So normally for this kind of questions, right, if you have no, if you know that you have a constant half-life, usually you will have to make use of it to check the time taken. So since half-life is a constant, what you will need to do is find out the number of half-life to reach 10%, and the time taken will be half-life times n, the number of half-life. So normally many people like to do halving, like you take the start, if I start with 100%, one half-life, I get it down to 50%, and so on and so forth. I've got 25, 12.5, and then finally 6.25. You will notice that sometimes this doesn't work because over here 10% is not the value you can get by halving your original, it is actually your half-life is not the whole number. So when your half-life is not the whole number, no choice, you have to use the formula, and which all of you should learn. Okay, so this is the formula that we are using. Okay, so we have out of 100, the final is about 10%. So the proportion, in terms of proportion, it is 0.1 over 1. Okay, multiply by, this is equals to half to the power of n, where n is the number of half-life. Okay, so other than proportions, do take note that you just need to make sure that you equate the half to the power n to some final value over the original. Okay, this is what you usually do. It doesn't have to be this ratio, final over original, doesn't have to be always the proportions. It can be in terms of percentage, it can be in terms of concentration, so concentration of final over the original concentration. This will also work. Okay, so once you work this out, you will be able to find that n is equals to 3.32. You will need to be able to solve for n, and the time taken is therefore 3.32 times 10.8. Right, so this is your final answer in minute. In the next part, we want to look at the half-life of NO when concentration of Cl2 and NO are double. Okay. So to do this, we go back to our rate equation again. We know that regardless of the experiments that we're doing, we are always keeping a concentration of chlorine being a constant. So let's say I do an experiment with one concentration of chlorine, I make sure it is constant. When I repeat the experiment again, I will repeat with another concentration of chlorine. But during the experiment, I will make sure that the chlorine concentration is a constant. Okay? So this is what we meant. So since my chlorine concentration is a constant during any experiment itself, I can group it together with K, remember that? So I will say that this is actually a pseudo first order reactions where the T half is equals to ln 2 over K prime. Okay, take note, this is K prime, not K, because T half equals to ln 2 over K, it apply only to a first order rate equation. So, but in this case, my ln 2 over K, the K prime is K prime, right? So it is actually my K times concentration of Cl2. With this, we can now look at the question. When concentration of chlorine is double, I will see that my T half will be half. Okay, this is a mathematical relationship which I can see from this math equation. Okay, so since T half is half, so that means T half equals to half times 10.8, which is equals to 5.4 minutes. What about NO concentration? If I double the NO concentration, there is no change to T half because my expressions of T half doesn't include NO, right? So I will be able to see that, okay, T half is remain at 10.8 minutes. Please take note, the question says state the T half. State the T half. So you need to give the numerical value. You cannot say that when NO concentration is double, T half has no change. That will not be accepted. You need to state the T half, all right, the values. Okay, so this is what I meant, 10.8 for NO concentration change, 5.4 for chlorine concentration change. In the next sections, we have another experiment now. This is reactions between carbon monoxide, NO, with oxygen gas, all right, to form nitrogen dioxide. They give you some detail for the reactions. They tell you that, it takes place at a constant temperature and with the same partial pressure of oxygen for each of the experiments that you have repeated. Now, the purpose of telling you all this is really to emphasize that the change in the rate, okay, any changes in the rate when you do a comparison between experiment, it is due to the change in partial pressure of NO. It has nothing to do with the partial pressure of O2. It has nothing to do with the temperature. So the rate constant K remains the same. So looking at the results, we want to use the results to determine the order of reaction with respect to partial pressure of NO. Okay, so you need to use the results to plot a suitable graph. Now, remember, to find the order of reactions, we will need to figure out how the rate changes with the concentration of the reactant. So partial pressure does indicates the concentration. So in fact, it is directly proportional to the concentration of NO. Okay, so partial pressure square, that is directly proportional to the concentration square. Now, just a side note, some of you might be wondering, how do I know that the concentration is directly proportional to the partial pressure? I can show this by using the ideal gas equations. So applying it to the partial pressure of NO multiplied by the volume equals to amount of NO times RT. So rearranging this, partial pressure of NO over RT, this is equals to amount of NO over volume. So can you see that this is now concentration of NO? But this concentration is in terms of mole per meter cube, and not dm cube, but meter cube, because that's the unit we use in our ideal gas equation. But it's all right, we know meter cube or dm cube, they are directly proportional relationship. So what kind of graph are we plotting now to determine the order with respect to NO? We are actually plotting, we will need to plot the rate concentration graph. Okay, but you have two set of value. So should you be plotting rate concentration or rate concentration square? Okay, so that is a choice you need to make. Now, personally, I would like to choose the one with a straight line because that is going to be the easiest to manage in terms of explanation. If you unfortunately choose the one that gives you a curve, not to worry, you can still salvage and make do with it. But really, for rate concentration graph, it will be really nice and easier if you just have a straight line. So to figure out which is a straight line, you don't want to replot many times. My suggestion is you do an inspection. You can do an inspection of the data, which I did, to see which one is more likely to be give me a linear straight line graph. Okay, so I will see that it is actually graph of rate against partial pressure square. For those of you who don't like to inspect, you can use your graphing calculator to plot 3 points. Take the first point, last point, and some point in the middle. It should give a linear relationship. Okay, so you can use your graphing calculator to help you. So how do I find the order of reactions with respect to the partial pressure of NO using the graph? Let's look at the straight line graph first, rate against partial pressure square. So this graph shows us very clearly that the y-axis is rate, right? So my rate is directly proportional to the partial pressure of NO square. So what else can it be? This has to be, because it's passed through the origin, so I know that this is going to be my relationship for this equation. Rate equals to K times partial pressure of NO square. So I can see that this is a second order reaction. Okay, so to explain, you must tell me that it is a straight line graph passing through the origin. So the rate of reaction is directly proportional to the partial pressure square. Therefore, this is a second order with respect to partial pressure of NO. If you are using a curve, okay, you can still show it, but it will be a bit more tedious. Okay, so for me with a curve, I am going to choose two partial pressure 1 and 1 Newton per meter square. Then I double it. So I see that when my partial pressure is double, the corresponding rate will go from 190 to 760. So this change is actually times 4. It's a 4-fold increase in rate. So because of that, I will know that my order of reaction is equals to 2 with respect to partial pressure of NO. And the reason is because the rate is increased fourfold when partial pressure of NO is double. Part F deals with a new series of experiment. You are told that the partial pressure of oxygen was half. Remember earlier on when we did a similar experiments, we are told that we use the same partial pressure of oxygen. So now we have it half, right? So the purpose of halving and changing the partial pressure of O2 is for us to find the order with respect to oxygen. Okay, so if I can to find the order, I must know when I halve the partial pressure of oxygen, how does the rate of reaction changes. Okay, the clue given is the gradient at each point was half. So let's now look at the graph we had earlier on. Okay, remember the same rate partial pressure square. This is partial pressure of NO square, right? So we have used, so the blue line shows us the original one with a certain partial pressure of O2. So in my new series of experiment, I have to do it with half of my partial pressure. And my gradient is going to be half, okay? So to do that, you can just look at the last point over here, okay? All right, the last point. If you try and check, the gradient of this new line is half because when I look at change in y over the same change in same change in x, this is gradient is actually half of my original. Okay, gradient is half of my original. So I just need to read off from the last point, and I will be able to see that when it is half, my partial pressure is 380. When it is at the original experiment, this is actually 760. Okay, so halving the partial pressure will actually cause my rate to be half. Okay, so this is times half. Over here is times half. So with this relationship, okay, I know that this is going to be a first order reaction because my initial rate was also half. Next part, to construct the rate equations using the for the reactions between NO and O2. Remember, we have already deduced the order of reaction with respect to NO and O2. They are actually second order and first order respectively. So these are the power for your partial pressure term. Do take note that square brackets are not allowed. Okay, so if you have used square brackets in the rate equation, please mark yourself wrong. Okay, you should be using a round bracket, okay, for partial pressure. Okay. To work out the units of the rate equation, this is what you will need to do. First, you will need to rewrite your rate equation to make K the subject. So put K on one side, throw rate and all the partial pressure term to the other. And using this expression, we can now work out the units for K. So what is the unit of rate? If you go back to the table, you can see that the unit of rate is Newton per meter square. And per second, it is per second, yes. Okay. So this is per second. And the partial pressure used is your in terms of Newton per meter square. And I have altogether two pressure from NO and one more for the oxygen gas. Okay, so altogether 3 units of partial pressure Newton per meter square. Okay, so 2 plus 1 is the overall order of reactions. Okay, overall order of reactions based on how many pressure term you have in total for your rate equation. So once you see that, you can simplify, and you will get your unit of K to be per Newton square meter to the power 4 and per second. Part H, again, this is recall basic questions. You need to explain the term homogeneous catalyst. Okay, there are two things to explain over here. First is the word catalyst, and the other one is homogeneous. What is meant by homogeneous, right? So, yep, you will have a catalyst being a substance that increase the rate of a chemical reaction but remain chemically unchanged at the end of the reaction. Whereas a homogeneous, if it's a homogeneous catalyst, that means the catalyst is in the same phase as the reactant. Take note, it is same phase, not physical state, okay? Because a good example to show you that is oil-water mixture or any immiscible liquids. They are in different phase, although they are all physically liquid state. Next part, we are going to use the concept of activation energy as well as the Maxwell-Boltzmann distribution curve to explain why adding catalyst will speed up the chemical reaction. So Maxwell-Boltzmann distribution curve, this is how it looks like. Now what does it mean, all right? So Maxwell-Boltzmann distribution curve show us the number of particles with a specific amount of kinetic energy, all right? So do take note that here, the curve start from 0. It shouldn't start from anywhere because according to kinetic particles theory, all particles are in constant random motions. Okay, that means all particles must have kinetic energy. There's no particle with 0 Ke. So when we have a catalyst, the activation energy will be reduced because catalysts provide an alternative pathway with lower EA. Right? So this is the activation energy for the catalyzed reaction. We can see this is lower than the EA for the uncatalyzed reaction. Okay? This is for uncatalyzed reaction. So the area under the curve, okay, the area under the curve tell us the number of particles with kinetic energy greater or equals to EA. So looking at this, if we are looking at the purple shaded region, okay, this will give us the particles with kinetic energy greater than or equals to EA for catalyzed reaction. The part shaded in green will be for uncatalyzed reaction. Notice that you have more particles with this minimum energy required if it is a catalyzed reaction. Okay, so you need to put all this in words. Okay, so we have mentioned that just now. A catalyst provide an alternative reaction pathway with lower activation energy. The outcome of this, which we can see from the distribution curve, is that I have more particles, more reactant particles in fact, with the energy required for an effective collision. Okay? And therefore, the frequency of effective collision increase. Okay, and therefore the rate of reaction is increased.